If your most sensitive keys lived in Azure today, how confident would you be in their protection, audit trail, and uptime? In this course, we'll go from zero to enterprise, turning HSM concepts into clear designs, compliant operations, and defensible decisions. We'll move in 4 stages. First, you'll build solid HSM and cryptography fundamentals in the Azure context. Next, we'll compare Azure HSM options. Then we'll go hands-on with labs. Finally, we'll tie architecture, operations, compliance, and real-world decision-making together. We're going to work from risk to reality. We'll begin by clarifying why keys matter, what must be protected, where trust boundaries sit, and which workloads are regulated. From there, we'll map those needs to Azure choices like Key Vault, Managed HSM, or Dedicated HSM. Next, we'll practice how to operate them securely, including access control, lifecycle management, and monitoring. In the last step, we'll pull everything together into an enterprise design that produces solid, repeatable compliance evidence. Think of this course as a toolbox, not a movie you watch once. Beginners should move step by step and not rush past fundamentals. If you're experienced, focus on the services and scenarios that match your environment and keep connecting each concept back to a real workload you own or support. An HSM or hardware security module is like a tamper-resistant vault for your cryptographic keys. It doesn't just store keys, it securely generates them and performs encryption and signing inside the device. Organizations rely on HSMs to prove trust, meet strict compliance rules, and reduce security risk long before they even choose a specific Azure HSM option. You can think of a hardware security module as a heavily guarded vault for your cryptographic life. Instead of letting applications handle keys directly, the HSM generates, stores, and uses those keys inside a hardened boundary. Applications send data in, request an operation, and get results back. But the raw keys never leave. That separation dramatically reduces the risk of theft, misuse, or accidental exposure, and becomes a central trust anchor for your security architecture. Consider a database that's secure because it's encrypted, but the application keeps the key in a config file. A developer accidentally commits that file to a public repo. An attacker finds it, pulls the key, and suddenly every encrypted record is readable. The algorithm didn't fail. Key protection did. HSM has addressed this by moving keys into a hardened device, so applications can use keys without ever directly handling them. When an application needs a key, it doesn't generate it itself. It sends a request to the HSM. The HSM uses a strong hardware random number generator to create the key inside its secure boundary. Then it applies policy, key size, algorithm, allowed operations, and whether the key is non-exportable. Finally, the key is stored and used only inside the HSM, so applications get cryptographic services without ever handling the raw key material. Here, the HSM acts like a cryptographic service, not just a storage vault. Your application sends it requests. Encrypt this data, decrypt that token, sign this message, verify that signature, wrap or unwrap this key. The HSM runs those operations internally with its protected keys, then returns only the result. Because the raw private or master keys never leave, even a compromised server or detailed logs won't expose them. Access policies strictly control who can call which operations. Now let's focus on why an HSM is trusted in the first place. Tamper-resistant hardware makes it difficult to open, probe, or modify without detection or zeroizing keys. Logical isolation limits which admins and applications can even interact with it. Clear security boundaries separate where keys live from where code runs, reducing attack paths. And certifications like FIPS or common criteria provide independent assurance that these protections meet formal standards. HSMs appear anywhere a critical key needs stronger protection than software alone. They're often the root of trust for encrypting sensitive databases and applications. They sign documents, code releases, and high-value transactions, so unauthorized changes are instantly detectable. They guard certificate authority keys, which anchor your entire PKI. They also secure payment cryptography, tokenization systems, identity platforms, and emerging regulated AI workloads where proof of origin and integrity really matter. Here, The key idea is that one protected private key can power many trust decisions. The private key never leaves the HSM. All signing happens inside. Certificates, code, documents, and identity tokens are produced from that secure core. Everyone else only sees the public key and the signatures. They can verify authenticity and integrity, but can't forge anything, because they never control the private key. In regulated environments, the question isn't just, are my keys encrypted, but can I prove they're tightly controlled? Standard key storage often means keys can be exported, shared by admins, and only partially logged. With HSM-backed protection, keys are generated and stay inside certified hardware, access is policy-driven, and every operation is auditable. That higher assurance is what healthcare, finance, government, and regulated AI workloads rely on for compliance and trust. HSMs matter because they turn policy into enforceable controls. They let you split responsibilities so no single person can abuse key access. Every sensitive key operation is logged, so auditors can trace who did what and when. Keys stay inside the device, which strongly supports non-exportability and custody requirements. Together, these capabilities map cleanly to frameworks like PCI DSS, ISO 27001, SOC2, HIPAA, GDPR, and NISTs. But they still depend on solid governance and processes around them. You've seen that HSMs exist to keep keys inside a hardened boundary, tightly controlling how they're created, stored, and used. That lets you reduce exposure while still enabling trusted encryption, signing, and compliance-heavy workloads. In the next section, we'll build on this by covering core cryptography and key management concepts that you'll apply directly to Azure HSM choices.